SwayamPrabha. Digital India. Educated India.
Good morning, everybody. Today we will discuss about methods for solving steady-state conduction. So, this method is one of the direct methods, and direct methods are having little edge over iterative methods since round of errors do not exist and it involves predeterminable number of operations. So we'll start with a simple problem. An example, see, it's a domain where we have divided the domain into 6 by 6 or points or 5 by 5 cells. So in I direction or X direction, we have I count 1, 2, 3, 4, 5, 6. That means 5 cells. And in Y direction, we have J count, J equal to 1, 2, 3, 4, 5, 6 and 5 cells. So 5 into 5, 25 cells are covering this region. And this is a square domain, and on the domain boundary we have Dirichlet conditions, and this domain is divided in such a way that delta x equal to delta y. So if we can write the finite difference equation for each point in the domain, then we will be able to assemble those finite difference equations in the form of a system of algebraic equations. And here what we have described, that at the boundary conditions are known in terms of the dependent variable directly. These are called Dirichlet conditions, and in parametric form we will call them AXY, 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 AXY. These are known. So that means on this domain we have 6 by 6, 36 points. So at the boundary points values are known. That means we have to write equations for 1, 2, 3, 4, 1, 2, 3, 4, 4 by 4. That means 16 unknown temperatures we have to find out, because at the boundary points temperatures are known explicitly. We have imposed Dirichlet boundary conditions. So we have to determine temperatures at internal points, and we have to find out temperatures from 16 simultaneous linear equations. Because we have 16 points, we will write 16 equations, and from there we will find out 16 unknown t's. So the governing equation, obviously Laplace equation, del 2t del x2 plus del 2t del y2 equal to 0. we discretize following central differencing: ti plus 1j minus twice tij plus ti minus 1j by delta x square, tij plus 1 minus twice tij plus tij minus 1 by delta y square. By mistake, this has been written delta x square, but since we have taken delta x equal to delta y, ideally all of you know this is delta y square, but since here we are taking delta x equal to delta y, we can write delta y equal to delta x. So now we can get, if delta x equal to delta y, that we have already substituted, and then we can write, but ideally, as I mentioned, since this is central differencing in y direction, this is delta y square. Since we have taken delta x equal to delta y, we have written, we can write this term as delta x square. So then we will be able to write ti plus 1j plus tij plus 1 plus ti minus 1j plus tij minus 1 minus 4 tij equal to 0. So for equal delta x and delta y, when delta x equal to delta y, we can write this as the governing equation for every tij point. So if we consider any point here, we can definitely express the differential equation at that point in terms of its four neighbors and the point itself. So let us proceed further. Mathematically, what we are trying to do, we are trying to write down equations in this form: a11 t1 plus a12 t2, a13 t3 plus a1n tn, and all the simultaneous equations in this way, in this format, so that right hand side quantities are known and it becomes a system of equations where we will get a coefficient matrix, we will get unknown vectors, and we will get on the right hand side the known vector. So as I mentioned it earlier, that the governing equation for each internal node, now it will be ti plus 1j plus tij plus 1 plus ti minus 1j plus tij minus 1. So that means its eastern neighbor, its northern neighbor, its western neighbor, and its southern neighbor of the point of interest. And then we will be able to form this algebraic equation for each point. So point 2, 2, that means this point, what we have done, we have written a21, that means here the value is known, we have written a21 plus this is a12, this is a12 point, and this is a21 point. So a21 and a12, these are known, plus t32 plus t23 minus 4 t22, minus 4 t22, and this is the equation for point 22, and we then rearrange it in a convenient way and keep the known terms on the right hand side, unknown terms on the left hand side. Similarly, at the point at the point 3, 2, we write A31 plus T22 plus T33 plus T42 minus 4 times T32. And again, we transfer the known term on the right hand side and rearrange these terms, unknown terms, and that means unknown temperature, with their appropriate coefficients on the left hand side. Similar way, we write equation at point 4, 2, that means this point. This will be A41, which is known, plus A32, this point, plus A43, that means this point, plus A41 plus A32 T32 plus T43 plus T52 minus 4 T42. 4 minus 4 times T42. So this is the equation. Again, the known term we move to the right hand side, and unknown terms we rearrange on the left hand side with the appropriate whatever coefficients they have with those coefficients. Now we come to the point 5, 2. Here, this point, that means A51 and A62, these are boundary points we have written. Otherwise, A42 and A52, A42, A53, these are added, and then minus 4 times T52. So minus 4 times T52. Again, we move the known terms on the right hand side, left hand side, the unknown terms. So this way, if we write governing equations, at each point we will get the system of equations, and those system of equations, as I mentioned earlier, we can describe, or we can express as a coefficient matrix into Tij unknown values equal to the known values on the right hand side, arising out of Dirichlet boundary conditions. So, and here we can see mostly these coefficient matrix, what we obtain, this coefficient matrices will have diagonal dominance. That means we'll get one principal diagonal, and since it is Laplace equation, we'll get two subdiagonals with non-zero elements and two superdiagonals with non-zero elements. Remaining all the elements will be zero, and these are called sparse matrices. And we have already seen that if we get a tridiagonal matrix, solution technique is very easy. We can use Thomas algorithm, and we can get the solution very easily. For such pentadiagonal matrix, what we can do, we can easily adopt Gaussian elimination method, but there is another very efficient method which is like Thomas algorithm, very well appropriate matrix solver for pentadiagonal matrix. So for pentadiagonal matrices, we can adopt Crowd's algorithm, or we can follow Gaussian elimination method. Whatever you prefer, you can do that. I will give, if needed, a special lecture on Crowd's algorithm, like we have discussed Thomas algorithm earlier. So, what we can summarize, whatever we have done till now, that we will be following for steady state conduction problems, finite difference method. In the finite difference approach, the conducting region is covered with a grid consisting of intersecting lines. The points of intersection are called nodes. For a rectangular region, the grid lines are drawn parallel to the boundaries. For simplicity, the spacing delta x and delta y are chosen so that delta x equal to delta y. These are so chosen. Nodes are identified by double subscript notation ij, where I and j count the grid lines along x and y coordinate directions respectively. The node ij, which represents a particular subvolume, is presumed to be isothermal at temperature Tij. That means the node temperature Tij with its zone of influence will have the same temperature Tij. So now we can call these are usual internal cells. These are cells falling on the boundary and maybe subjected to uniform heat flux. Such nodes will be falling or fall at internal corner. We can call internal corner node. Such nodes are external corner nodes, and the domain may be such that it is surrounded by a fluid, cooling fluid if it is a heated body, or fluid may be used to heat up the body also, depending on the situation, and that temperature is T infinity, and the film heat transfer coefficient is H, and delta x is the grid dimension, and as again here delta x equal to delta y, otherwise delta y is the grid dimension in y direction. Now, as we said, that we will discuss how to write governing equation on such various type of nodes. First, we will take up for the internal nodes. Derivations are based on, again, simple assumptions that each node represents certain region. Its temperature is given by, like Tij is Ti plus 1j plus Ti, we have already found out that Tij plus 1 plus Ti minus 1j plus Tij minus 1 divided by 4. Eastern neighbor, western neighbor, northern neighbor, southern neighbor by 4, since these grids are equidistant grids, and delta x equal to delta y. That is number 1, all the delta x's are same and all the delta y's are same, which is called uniform grid. The temperature Tij at any nodal point may be viewed as the average temperature of the surrounding marked area, like average temperature of this marked area. And here you can see each marked quadrant has covered 1/4 of the neighboring cells. So 1/4, 1/4, 1/4, 1/4, like this is full cell volume having Tij temperature as the average temperature of the surrounding marked area. Now let us consider the node corresponding to the, first we will consider a internal corner. This node may be assumed to represent 3/4 shaded section. So as if this temperature will be the temperature of this shaded section, and exchange energy through convection with the adjoining fluid T infinity. Conduction to the nodal region Ij will occur along 4 different nodes. That means in this region, conduction will be counted from this node, 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 and the fluid temperature at T infinity, convection, heat transfer, exchange with the fluid. So that is how we will calculate temperature of this node. Now let us see how to do that. So we can see Q conduction. We have said first we will calculate conduction from the neighbors. So K delta Y into 1, that is the exchange area, grid dimension in Y direction, and we will write T I minus 1j minus Tij divided by delta X into basically delta Y. Then from the northern neighbor, again K delta X into 1, the area through which heat transfer is taking place, Tij plus 1 minus Tij divided by delta Y, that is the gradient, plus K delta Y into 1 Ti plus 1j minus Tij divided by delta X. And here the surface area through which heat transfer is taking place is delta Y by 2, because half, this is a corner node. The 4 quarters are supposed to represent temperature Tij, but this part is not there. So heat transfer will take place through delta Y by 2 into 1 multiplied by Ti plus 1j minus Tij divided by delta X, that is the gradient. Similarly, from the southern node, K delta X is the transport area, delta X by 2 into 1 into Tij minus 1 minus Tij divided by delta Y, that is the gradient. And what is convection? Convection is H into first delta X by 2 into T infinity minus Tij, then H into delta Y by 2 into T infinity minus Tij. So basically we are getting the convection transport through this equation. Now, if we equate this conduction and convection, then we will get Ti minus 1j plus Tij plus 1 plus half Ti plus 1j plus Tij minus 1. Just this is algebra. A equal to B plus H delta x by k into T infinity minus 3 plus H delta x by k into Tij equal to 0. And again, although while writing the equation, we have used delta y and delta x, but as we know, delta x equal to delta y, we have equated that, and we have expressed everything in terms of delta x. So this is then Ti plus 1j, sorry, Ti minus 1j plus Tij plus 1 plus half Ti plus 1j plus Tij minus 1, this whole quantity by 2, H delta x by k into T infinity minus 3 plus H delta x by k into Tij. And that is a nodal equation for this Tij, which is interior corner. And we are getting H delta x by k in this equation. We can see this is heat transfer coefficient, linear dimension, thermal conductivity of the solid. So this is basically when H, the heat transfer coefficient, into the linear dimension, the length scale, divided by thermal conductivity of the solid, then this is basically BO number or Biot number, and this is based on grid dimension, so we can call this as grid BO number or grid Biot number. Now let us quickly look at the situation when node Ij is located at the plane surface with convection. So this is again a plane surface, and it is exposed to external fluid with temperature T infinity, and the film heat transfer coefficient is H. Here again we'll go for energy balance. First conduction, K, again delta y into 1, that is the cross section through which energy is conducted, Ti minus 1j minus Tij divided by delta x, the gradient, then plus k delta x by 2 into Tij plus 1 minus Tij by delta y, gradient in y direction, plus k, again delta x by 2 into 1 multiplied by Tij minus 1 minus Tij by delta y, and then convection is H into delta y into 1 into T infinity minus Tij. So from here we can again simplify it as twice Ti minus 1j plus Tij plus 1 plus Tij minus 1 plus twice H delta x by k into T infinity minus 2 H delta x by k plus 2 into Tij equal to 0. So this will be the governing equation for one such point, which is basically located at the plane surface with convection. And if we have, if the medium is such, that means the material is such, where uniform volumetric heat source is present, then this equation can be further modified as twice Ti minus 1j plus Tij plus 1 plus Tij minus 1 plus twice H delta x by k, same, into T infinity minus again 2 times same, 2 times H delta x by k plus 2 into Tij plus this volumetric heat source into delta x square by k equal to 0. And again delta x equal to delta y. So this will be the governing equation. If there is volumetric heat generation rate or volumetric heat source is present in the material, so this will be the governing equation. Now let us look at in the same way it can be shown the way we did the energy balance, the governing equation for a node which is located in such a way that it forms external corner. And if this external corner node is identified as Ij, then Tij, how to express? Tij minus 1, that means this temperature at this point, plus Ti minus 1j plus 2H delta x by k into T infinity. T infinity is the local temperature, fluid temperature, minus 2H delta x by k plus 1 into Tij. So this again the same way energy will be conducted from this node to this node, this node to this node, and energy will be convected from this side and from this side. So we have to take care of the sign convention and perform the energy balance in a correct way to get the governing equation with the approximation or with the assumption that we are following delta x equal to delta y. Now let us solve quickly an example to whatever we have discussed so far. A 2D plate of a given material is having 1 meter by 1 meter dimension. 3 surfaces of the plate are maintained at 600 K, this surface at 600, this surface at 600, this surface at 600 K. Remaining surface is exposed to airstream 300 K, and using delta x equal to delta y equal to 0.25 meter, determine the temperature distribution, internal temperature distribution. H equal to 10 watt per meter square Kelvin, and K of the material is 300, this 300 K, sorry, this is not lowercase k, this has to be uppercase k, 300 K Kelvin. So temperature of the K of the material is 300 K. Please, consider this K as uppercase K, as capital K. So 300 K K of the, we have written also here 300 K airstream, and K of the material at 300 K is 1 watt per meter Kelvin. This is the thermal conductivity of the material, 1 watt per meter Kelvin, poor thermal conductivity. So maybe this is some insulating material where we want to find out the temperature distribution. The grid consists of, then if we have this grid size, we can easily calculate, we'll have 12 points. but using symmetry about the mid plane, because this side and this side same, this side is 600, this side is different. These two symmetries, we can have this vertical symmetric line, vertical midplane around this. These are symmetric. The number of unknowns are reduced to 8. So whatever is temperature here, if we consider symmetry, will be temperature here. Whatever is the temperature here will be the temperature here. Whatever is the temperature here will be the temperature here. And so instead of solving at 12 points, now we have to solve at 8 points, because this 1, 3, 5, 7 will be repeated on the other side. Now for node 1, here or here, it is same. We can write, for example, if we consider here, T2 plus T3 plus 600 plus 600, 1200 minus 4T1 equal to 0. And here again, we can rearrange minus 4T1 plus T2 plus T3 equal to minus 1200. Now at node 3, we can write T1 plus T4 plus T5 plus 600 minus 4 times T3 equal to 0. Again, we can rearrange and place this minus 600 on the right hand side. Then at node 2, this will be twice T1, T1 plus T1 plus T4 plus 600 minus 4T2 equal to 0. And we can rearrange again as twice T1 minus 4T2 plus T4 equal to minus 600. Let us look at another node, node 5, which is T3 plus T6 plus T7 plus 600. This is 600 minus 4 times T5 equal to 0. So we can write T3 minus 4 times T5 plus T6 plus T7 equal to 600. So this way, I'm not repeating the same way of calculating at node 4 and node 6. These are same, all internal node. You can see we have calculated here 1, 2, 3, 4 up to 6. These are all internal node. Now these two nodes are falling on the boundary, so we have to have a little special treatment. So for node 7 and 8, we have to make use of relationships that we have just derived. So at node 7, it will be 2 times T5 plus T8 plus 600 plus, this is 2, this is H, this is delta X by K into T infinity, minus again 2 times H delta X by K plus 2 into Tij, here it is T7. So we get this equation. Node 8, again we can write 2T6 plus 2T7 plus 2 into H into delta X by K into T infinity minus 2 times H delta X by K plus 2 into Tij, which is T8 here. And we'll get this equation. And we have rearranged the equations in such a way that all known quantities are on the right hand side. So we can now form a matrix, coefficient matrix, into unknown vector equal to a known vector. And coefficient matrix will have the coefficient of the coefficients of the temperatures of the unknown points. Like if we go, our first equation will be 4T1 plus T2 plus T3. So T1 will have a coefficient minus 4, T3 will have a coefficient 1, T2 will have a coefficient 1, T3 will have coefficient 1, T4 to T8 are absent here. So we'll write 0 as their coefficients and we'll write minus 1200 on the right hand side. So minus 4, 1, 1, 0, because we do not have in that equation, in the node 1, we do not have T4 to T8. So all are 0. And then this is the, with this column vector, if we multiply the row, we'll get the original equation. Right hand side is 1200. So this way, row by row, we reconstruct or construct this Ax equal to B type of system. This is the coefficient matrix. This is the unknown vector, unknown temperature equal to right hand side known quantity. So again, solution of this system of equations can easily be obtained by inverting this matrix. We would like to discuss about a few more conditions which are important, but in this typical example or the cases we have taken up so far, we have not mentioned about it. This is for insulated boundary. So if the boundary is insulated, then again we'll do the same. Ij is a point of interest. Ij plus 1 is the northern neighboring point. Ij minus 1 southern neighboring point. I minus 1j is the western neighboring point. And then we will consider Q1, Q2, Q3, Q4 to this node. Q1 will be given by, it is by conduction, K delta Y into T I minus 1j minus Tij by delta x. Q2 is also by conduction, K delta x by 2 into Tij minus 1 minus Tij by delta y. But Q3, since it is insulated surface and this node will not receive in energy from this side, so Q3 is 0, and Q4 is K, again delta x by 2 into 1 into Tij minus j plus 1, sorry, Tij plus 1 minus Tij by delta y. This is the del T del y gradient. And then we sum up Q1, Q2, Q3, Q4, and that will be 0. We can write this, and from here we can write twice Ti minus 1j plus Tij minus 1 plus Tij plus 1 minus 4 times Tij equal to 0. This is the equation for this node if it is located on in such a way that it faces insulation on its side. That means the surface is insulated and this node is located here, whereas the right hand side is insulated. Now, if there is volumetric heat generation at a rate of Q star, the nodal equation will become then twice Ti minus 1j plus Tij minus 1 plus again Tij plus 1. These will be repeated, will remain same. Minus 4 Tij, again this will remain same, plus again due to presence of volumetric heat source, we will add up this term Q star delta x square by K equal to 0. So this equation is modified with an additional term plus Q star delta x square by K. All these 4 terms plus Q star delta x square by K equal to 0. If we have volumetric heat generation within the material. Otherwise, this is the governing equation on a node which is located at insulated boundary. So with this, we are concluding our lecture today. Basically, we have observed how the steady state heat conduction equation, which is basically Laplace equation, is solved on a given domain. Thank you very much.